All right. On the quiz, you absolutely are going to have to do a problem like number 12. For sure. Okay? I promise you. So it's always frustrating to me when we get to the quiz and people lose points on the piecewise function, because I told you it was going to be on there. It's going to have circles in it and your lines, and you're going to have to be able to do that. So you've got to know that the equation of a circle is this, okay? And this is probably the last one we'll practice between now and Thursday. So, you can make them up. You can draw a picture like this yourself, and you can just make them up, right? And it's not hard to do. Now, I will say, and somebody asked in the other class, and I told them about this. This is a mistake here. I don't know how you looked at that. The picture, the blue, when they printed the book, it got off. I'm not going to make you guess at what that is. That's supposed to hit right there. That hits right there. This is supposed to be the center right here, and that's a radius of 3. Okay, so I'm not gonna make you try to guess at what those points are. Okay, so this circle has the center at 0, -2. So that'd be y plus 2 squared, and then the radius is 3. Where radius is 3, so 3 squared is 9. Okay, what do you have to do after that? Solve for y. You've got to get in terms of y equals, because our answer is going to be f of x, or whatever they told you to call the function. Did they even say? They didn't really say. Okay. So we've got to, that's y equals right there. So we've got to get ours in terms of y equals. So this would be just plain old x squared, so I'm going to move that over. So we have y plus 2 squared equals 9 minus x squared. Okay. And then we're going to square root both sides, and so we're going to get y plus 2 equals plus or minus the square root of 9 minus x squared. And no, you cannot square root those and get 3 minus x. It doesn't work. You just got to have that. Do we want the plus or the minus? Because that's the top half of a circle. Doesn't matter that it's below the x-axis and part of it's negative. It doesn't matter. The plus on the square root is the top half of the circle. The negative is the bottom half of the circle. We've got the top half of the circle. We don't have the whole top half, but that doesn't matter. It's the top half of the circle, so we want the plus on the square root, so we'll get rid of the negative. And then we're going to subtract 2. So I usually put that in front, so it would look like this. Okay? So now let's write our equation. So that's one of the equations. So typically when I do a piecewise function, I don't start with this. I do all my work, then I stick them in there. Okay, now that's not the way I did it the other day. We went line by line and I put them in there, but I did do my work off to the side. But that's my equation of my line now, or my circle. Now let's do this line. What's the equation of that line? That's y equals -2. So I'm done with that. That's easy. And then what's the equation of this line? Well, this has a slope of what? -2. Looks like it has a slope of -2, so that'd be y equals -2. And then let's pick a point. Here's a good one to pick right here. This would be a good one to pick. A lot of you would probably pick that one, 2, 2. So let's pick that one. X minus 2 plus 2, right? We do the point slope form, okay? And then you don't have to even do anything with that. You could distribute it if you want, if you like to. I know some people do. So if you want to do -2x plus 4 plus 2, which would be -2x plus 6, y equals -2x plus 6. So if you want to do that, then do that, right? I mean, that's a danger. The danger is you don't do it right. Oh, wait, I wrote plus 6. I meant plus 2 there. I was thinking ahead, right? Okay, so -2x plus 4 plus 2, that'd be -2x plus 6. So if you want to do that, that's fine. But if you screw it up, then, you may have been better off just leaving it here. Okay, now let's start from the left to the right. So the first one is y equals -2. You just put a -2. That's all you put in there. And then that goes from where to where? -5 to -3. I'll include them both. Then my circle goes from where? Well, what's my circle? It's -2 plus square root 9 minus x squared. I don't use the y equals because I already got that here, comma, and then that goes from -3 to 2 right there. But I don't include the 2 because it's got the open circle there. Okay, and then I go to my line, which is -2x plus 6. or I could write this version of it, doesn't matter. And then that goes from 2, and it includes the 2, all the way to 5. Now there's not a circle here. We'll assume, if there's not an open circle, we'll assume it includes that endpoint. Okay? All right, so you've got to be able to do that. That'll be a problem on the quiz. Now, did they ask for the domain and the range or anything on that? Or did they say just graph it? They said, or not graph it, but just find the formula, right? That's all they wanted you to do. Now, if they would have said, what's the domain and range? Maybe that happened on a later question, didn't it, on 28. On 27 and 28 there, on 28 it talked about that. But let's say they asked for the domain of this. Right? Wasn't this your domain right here? Isn't that part the domain? When you think about it, that's the domain. Okay? Now, you probably wouldn't write it like that because it goes from -5 and then it goes all the way to 2. So when you wrote it, you'd probably write -5 to 2, like that. Right? But wait a minute, it keeps going, doesn't it? It doesn't really stop at 2. This one does, but then it picks up at 2, right? It keeps going. So actually, this one's just -5 to 5, isn't it? Right? So when I say that this is your domain, it's in pieces, but the pieces actually continue and they include everything from -5 to 5. So actually you should write your answer like that, but it came from that right there. Now it's possible we could have had a gap here. You know, what if this piece wasn't here and it just would have went there, right? Then we'd have went -5 to 2 and then went from 3 to 5, right? So we could have had 2 pieces we'd have had to write there. And then, and if that's the case, you'd have just went -5 to 2, not include the 2, and then you'd went 3 to 5. You know, if it had been like I drew right there, then that would have been your domain, right? Okay, all right. And then what's the range on this one? What's the range on this one? It's easiest to look at your graph to do the range. Again, start with little, so start down here. So -4 all the way up to 2, right? Even though there's a hole there, that doesn't matter. It hits all the y values from -4 up to 2. It's all those y values. So -4 to 2 would be the range, right? Okay, so domain range, got to be able to do that. You're going to be asked some questions for sure on the next quiz about domain and range. Okay. Oh, shoot. Okay, that's getting into my next stuff. So, 19. You guys were wondering about 19. All right. This question is a little bit of foreshadowing, not something you're going to have to probably do from scratch like this on the quiz. Okay. Just got to tell me number 12 and beyond. Got to be able to do number 12. Okay. 19, this is a little more looking ahead at some stuff we'll be doing, but you've got to be able to read a question like this and break it apart and see what it's telling you. Okay. And this is new and this is a little trickier, but they tell you that L, the function L is 2x plus 1. And then they said, let A of t be the area of the trapezoid bounded by blah, 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 blah. Well, think about what we've learned, the definite integral. What is the definite integral? Area. Area underneath the curve, right? That's what this is talking about. So when we get to that section where we're doing area, you're going to hear this a lot, okay? So what they've done is they've given you this function, so we need to be able to graph this line, 2x plus 1, so that's going to cross up here at 1. It's got a slope of 2, so it's going to go over, 1 and up 2, right? So it's going to be there, it's going to be there. Okay, that's enough probably to give me a picture, okay? So here's my line. So that's 2x plus 1. Now, they want a trapezoid that's bounded by 4 things. It's bounded by this line, it's bounded by the y-axis, it's bounded by the x-axis, and some line x equals t. Now, you know, the line x equals 2 is a vertical line, right? X equals 3 is a vertical line. X equals 4 is a vertical line. X equals t is some vertical line that can move and change and shift. We don't know where it is, but it's out there somewhere. Okay? So it could be at x equals 2, could be at x equals 3, could be at x equals 4, whatever. So we'll just label it as t. Well, there is your trapezoid, right there. Right? From there to there, bounded by those 4 pieces, bounded by the line L, bounded by the x-axis, bounded by the y-axis, bounded by the line x equals t. So that we need to be able to do. If you break that apart and look at each of those little pieces, we should understand those things. Vertical line, to be able to draw a line, the x, y-axis, whatever. Okay, they want a function that is the area of that red thing, where t is going to be the unknown quantity, that is the right edge. Think about it. As we change t, what happens to the area? It's bigger. Or littler if you come this way. But the bottom line is it's a function, right? Because for any input, for any vertical line t, how many areas are you going to have? One, right? Which is what you need for a function. One input, one output. So you move line t to a new spot, you get an area. Move it to another spot, you get another area. Okay? So we can write that function. Well, what is it? Well, it's 1/2 the sum of the bases. Okay? So what's this base right here? 1. Is that going to change ever? No. What's this base? That's the part that's going to be new for you guys. What's that base? Does it change? When that line t moves, isn't that base going to get bigger or smaller? So how can I figure out what that is? Yes. Think about this. If I told you this line was at 3, how would you figure out this? You'd plug a 3 into the line, and you get a 7. 2 times 3 plus 1. What if t was at 4? What would you get? 2 times 4 plus 1. Or if t was at 5, you'd get 2 times 5 plus 1. Well, what if t's at t? What do you get? Put t in the equation and you get 2t plus 1. This is something that people sometimes struggle with in the beginning here, but what do? You're going to plug a t in for x. Seems weird, plug one letter for another letter. That's what we do. We're going to plug t in for x. So we're going to plug t into the line equation, we're going to get 2t plus 1. That's that base. So we got base 1 plus base 2, and then times the height of the trapezoid. Well, this is the height, actually. It's a trapezoid tipped up on its end, so the height is actually down here. What is this length right here? Oh, come on. It's t, right? It's t. There you go. Just like that. So, now we can do a little simplifying. Actually, you could probably stop there, but if you want to compare your answer to the back, I'm going to bring that t around front with the 1/2. This would be 2t plus 2 in here. I'm going to distribute that. 1/2 t times 2t is t squared. 1/2 t times 2 is just t. Is that what they had in the back? Right? So you can see if I'm walking around and I'm looking at number 19 and all you've got is that, I'm thinking to myself, okay, well, I know what you did, right? I mean, you've got to, should really have a picture on that one. But there you go. So for any value of t, that is for any location of this right edge, this would give me the area of that trapezoid. All right. What else? 22. Is that talking about the absolute value function?
Yeah.
Oh yeah, what's the absolute value function look like? Right? This is the classic piecewise function. Isn't that a piecewise function? It's 2 lines. It's 2 lines. Now we don't think of it as 2 lines, we think of it as v, right? But what it is, the definition of absolute value is actually a piecewise function. The formal definition of absolute value. I know what you guys think. What's absolute value do? If I ask you, what would you say? Makes it positive, right? That's what we say. We describe it in words. But mathematicians cringe at that. We want a more precise definition of absolute value. Okay, and here's what absolute value is. So that's what you're saying in part C, right? The rule as a piecewise function. So let's do this piece, right? This would be the line y equals what? What's the slope of that? -1? Goes through 0? We don't even have to write it. It's just y equals -x, right? What's the graph of this piece? Isn't that just y equals x? Right? So really, isn't this the same thing we were doing over here, but just way easier? I mean, easier in the sense that the reason this is harder is we don't think of absolute values as piecewise functions, just two lines. One's y, so this is y equals, I wrote absolute value of x here, I could have just put f of x, but it's basically y equals, so think of that as your y here, right? Y equals that, same thing. -x, and that's when? Except, always go little to big. So -infinity to 0. Now, do you want to include the 0 or not? I usually would say we don't. Okay? And then it's x, it's y equals x, when we go from 0 to infinity. In other words, when x is positive, the absolute value function is just that number, x. When x is negative, it's the opposite. Right? So if you got -5, you want the absolute value, it's the opposite, it's 5. Okay, so that's how absolute value of x technically is defined, right there, as a piecewise function. Okay, so that's what 22 is talking about. All right, anything else? Anything else on there at all? Natural domain, when we talk about natural domain, like on 30, right? I mean, all they're saying is what are the x values? That's just like saying what's the domain. I mean, so don't worry about the word natural domain there. It's just what's the domain, okay? Well, it's what are your possible x values? Well, what can you put in there? What would be a problem here? That's usually the way I think about domain. What are the numbers that would be a problem? What's an issue with square root? 0 would be okay. 0 is okay. 4 minus 0 is 4. Square root of 4 is 2.
Well, you can't have anything that adds up to
0 is okay. Square root of 0 is 0.
Negative.
Below 0, you can't have any negatives underneath it, right? So when would this be negative? So if x squared is bigger than x squared. I like thinking of it as x squared. You're right, 2 because you're squaring it. But I like thinking of this and just saying, this piece better not be bigger than 4. We better not have 4 minus 5, for example. 4 minus 6, 4 minus 7. Right? Well, when will x squared be bigger than 4? Well, when x is bigger than 2 for sure. But also, when x is less than -2, right? Like -3 would be bad, -4 would be bad because that'd be 9 or 16. Right? So in other words, x better be between -2 and 2, right? Because if it gets bigger than 2, then you're going to get negative under there. If it gets littler than 2, right? And then the range is what? Now to do range, you just think, okay, now plug in any numbers you want. What kind of numbers are you going to get out? Well, what are you always going to get out of the square root? It's going to be positive, right? You're always going to get a positive out of there. Now, don't confuse this with when you have like x squared equals 9. When you solve a problem like x squared equals 9, you get plus or minus, right? You do plus or minus square root of 9. But if I just ask you, I told you this the other day, if I just ask you square root of 9, what's that? 3. Square root of 9 is just 3. It's not plus or minus. Square root of 9 is just 3. If I solve an equation like this where I do the square root of both sides, yeah, then I have to do plus or minus, like on the circle equation. Okay, so this is just going to be 0. So the only thing you're going to get out of here is positive numbers. Okay, is there a biggest? Is there a limit to the biggest thing you get out of there? I think there is, right? I mean, because if you only put in things between -2 and 2, so if you put a 2 in here, 4 minus 4 is 0, so you could get 0. So the littlest thing you can get is 0. But the biggest thing you can get, I think, is what? 2. If x is 0, you get square root of 4, which is 2. But I don't think you can ever get anything bigger than that. Okay? You're going to get, you're just not. You're going to. So it's just a matter of trying things, plugging things in, thinking about. The big ones, of course, are you can't have 0 on the bottom, and you can't have a negative inside of a square root. Those are the big ones that are going to limit you. All right, let's move on. Because I got several things, and I got some optional IXL stuff for you to do as well, depending on how much of this you want to talk about. So some notes there, how much of this you write down is totally up to you. There's a lot of terminology here in section 2. So like in the bold, in boldface, as you go through there, basically section 2 is about graphs. And the reason graphs are important is when we first learn our calculus stuff, which is going to be coming up here after our quiz on Thursday, so on Friday, we'll really be getting our first introduction to actual calculus things. Because really right now this first quiz is more just review of functions and function language. But graphs are where we're going to start. We're going to start looking at graphs. And so at the top of page 12, they've got this picture here, which we want to really get used to function language. So notice we're not using, we don't use y a lot. Okay, so when we're talking about an ordered pair, we're not going to talk about x, y as much as we're going to talk about x, f of x. Or in this case, a lot of times when they're talking about a specific point, they use a or b. Okay, so when you hear f of a, f of b, f of c, you want to think of those as y values. Now I'm going to say outputs. Okay, now they labeled that the y-axis and the x-axis. A lot of times they'll do this. They'll talk about a function and you'll see them write this. They'll just say your y, your output is the function s. Okay, but just understand that lingo. So A, B, and C are the inputs, the x's, f of A, f of B, f of C, those are the y values, the outputs. Okay, all right. So you see that, they talk about the vertical line test in there a little bit. Down at the bottom of page 12, continuous functions, talks about continuous. For right now, just worry about the word continuous means no breaks, no holes. Now, piecewise functions are classic discontinuous functions, right? If a function's not continuous, it's discontinuous. Like this graph here. That is not continuous. There's a break, there's a gap in that. But most functions we know about, parabolas, the sine graph, lines, they're continuous. Tangent would be a great example of one that's not, though, right? Or secant, the sine graph, the cosine graph are continuous. Tangent, though, is not continuous. It's got some breaks in it, some asymptotes, that kind of stuff. Okay? All right. So that's just some language you'll hear. You go over to page 13, talks about x-intercepts and y-intercepts. Talks about increasing, decreasing a little bit. Okay, moving on to page 14. A lot of bold-faced terms there. Talks about the roots of an equation, the roots of a function. How about this one right here? What's a root? What does that mean? Don't mix that up. It can be a solution to a certain thing, but just the root of a graph. Where am I looking? That's this point and this point. That is your x-intercepts. The roots are the x-intercepts. Now, when you talk about the solution, yes, that would be the solution to this equation right here. It's where the y values equal 0. So it's a solution to the function set equal to 0. Sometimes we call that the zeros of the function. They might even use that term in there. No, they don't. But the zeros of a function is the roots of the graph. So it's a little bit of a technicality. We're talking about the function, we call it zeros of the function. We're talking about the graph of the equation, we call it the roots of the equation. Okay, it's kind of a technicality. But we are very interested, we will be very interested this year in those points, right? When we look at graphs, we'll be very interested in where it crosses the x-axis. That will always tell us some information. So that's a special consideration. We might have to do some estimating on graphs, right? If we don't know exactly what the equation is, we might have to estimate some points, okay? They talked about something called a local minimum and a local maximum. This point right here would be what we call a local max point. A local max. Local means in that small vicinity, right around that point, that is the highest point. And down here's a local min. Think of local max and min as peaks and valleys. Okay? Now they don't use the term here. They do later on. We also have what's called a global max and min point. Now a global max and min point means the highest point on the whole graph, or the lowest point on the whole graph. So a graph can have, like here would be a graph that would have a bunch of different, if I stop this graph right here, it would have 3 different local max points, but only one global max point. Okay, there's the global max point, but those 3 would all be local maxes. Okay, peaks and valleys, local max and min. All right. And again, it talks about increasing, decreasing. Here's another term that's important: concave up and concave down. Now, don't confuse that with like convex versus concave. I don't even know what that means. We don't use the word convex ever here. Concave up or concave down. Which would you guess? Let me do it in red. I'm going to guess that from about here to about here, and I am actually just guessing, this piece here is one of those. It's concave up or it's concave down. Which one do you think? Which one would make the most sense? This is concave up. Concave up is like holds water, so it's the curve. So it doesn't have anything to do with increasing or decreasing. This graph is decreasing for a while, then it's increasing, right? Going down, then going up, but it's concave up that whole time. Now it switches here. If I switch to black, from here over to here, it's concave down. Okay, that's concave down. So here you've got this graph. It's on its way up. For a while, it's concave up and on its way up. But it switches to concave down. It's still going up, but it's concave down, curving down. You might think about speeding up and slowing down, right? It's going to have to do with slope. Think about it. Steeper, 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 and then all of a sudden it switches and starts getting less. Concave up, concave down. The place where that switches is called an inflection point. That point right there where it switches is called an inflection point. Okay? So at that point, there isn't any concavity. The graph is not concave up or concave down at that point. It's switching. Kind of like at a local max. You guys had that on that one worksheet we did. The local max and min, it's not increasing or decreasing at that point. It's not changing. Okay? That's where it's switching from increasing to decreasing. Okay. So a lot of terminology. All right, another thing you're going to have to be able to do is, and I told you this, so you're going to have to know those terms. You're going to have to be able to read a graph in context. Maybe on your calculator, maybe you type it into your calculator, maybe you're just given the graph. You have to be able to read it in context. Here's a problem, just talks about an epidemic, and it shows 3 different groups of people in the population. The people that are susceptible means they could get it. They haven't gotten it yet, but they could get it. So in the beginning, there's a lot of those people, okay? There's a small number that are infected, that's I, and there's a small number that have had it and are recovered, okay? As time goes on, what happens? The number infected goes higher. The number that then recover is starting to go up as well, and those that haven't gotten it yet starts to go down. At some point, the number of infected reaches a peak, and it comes on down. The recovered keeps going up and up and up. Okay, and then pretty soon there's not anybody left to get it. Okay, and so just be able to read a graph, be given the units, and be able to answer questions and talk about it. There's not a lot of studying you can do on that. That's just kind of common sense. Okay, but we want to be able to read. We want to be able to read graphs, and we want to be able to use function notation. So, like if I asked you if this was You know, we got 3 different functions here. So if I ask you S of 15, to approximate S of 15, what would you say? S of 15 is approximately what? How much? 4,000, right? You're just reading this Y value right here. Then if I asked you to tell me what that means in words, what would you say? No, not 15 people. On the 15th day of the epidemic, right? And let's talk in complete, if I was answering this on a quiz question, I want to see kind of complete sentences. On the 15th day of the epidemic, there were 4,000 people who are susceptible, have not gotten the flu or whatever the case is, right? So you would want to put that into words. Or if I said, what's the solution to that equation? You're looking for, oops, wrong graph. You're looking at that point right there, aren't you? Okay? You're looking at that point right there. And you would say 8 days, right? And then if I said, what does that mean? You'd say, what? On the 8th day. On the 8th day, there were 20,000 people susceptible. Okay, now what if I asked for I of X equals 20,000? Then, wouldn't you have 2 of them? Right? And what if I ask you, why are there 2 of them? Is that okay that there's 2 of them? Right? It doesn't violate being a function, right? Function, you have 1 input, can give only 1 output. But you can have, for 1 output, you could have different inputs, right? I mean, look at the sine graph. How many times does it hit 1? Right? It hits 1 an infinite number of times. So why is there 2 times? And then comes back down, right? There's 20,000 people infected on day 7, and then it goes above that, and then it comes back down on the whatever, 21st day, and it's on its way down, and there's 20,000. But it can hit it at different times. See, so be able to use the function notation, right? And be able to talk about it and be able to describe it. Okay, so moving along, on page 15, we talked about that table of data. We talked about a function being undefined. If you have a table, you only know those points. You don't know the points in between. So graphically, it could be any of those graphs. We don't know. We don't know. All we know are what those points are, right? So we don't really know what it is. All right, so the last big thing, well, several big things we want to talk about here would be the idea of moving and stretching and so forth with functions and dilation. So I've got an IXL here, and I thought I would just kind of go through this. We would talk about this a little bit, and then you can go through it yourself if you want to. There's a couple different ones. Okay, so let's just review this. You did this in advanced math. Okay, so if you have f of x map or switch to f of x minus 7, what does that do to the graph? Which one of these does it do? Is it up or down?
There was one that was the opposite, and there was one
That's when you affect the x.
That's when you affect the x. That's true. When it's on the inside, when it affects the input. So that's a great way to think about it. Is it going to affect the x or is it going to affect the y? Well, when it's on the outside of the function, that's the output. That's how I remember it. It's the output. It's the y. So this is going to go down 7. Now, another way to think about that is think about what this will do to the y values. Remember, f of x is the y values. So in this graph, you got this y value. On this graph, the y value subtracts 7. So it's going to be 7 less. The y value is going to be 7 less. So the whole graph's got to go down 7. So I think that's right. Okay? What's that do? 1 up, So that's what you were thinking of, right? Now your translation is inside the parentheses. It affects the input, and now that means it goes to the right 8. Okay? To the right 8. Now, why is that? It's always tough. I'm with you. I just memorize it, right? I memorize it. I'm like, but why is that? Well, here's why. If I put a 2 in here, think about this now. What this is saying is that this graph is shifted here. That means for this first graph, if I put in a 2, I'm going to get out something. Let's say German short here. Okay? On this graph, if x is a 2, what's 2 minus 8? -6, right? That means when I put in -6, I'm going to get that out. Right? It'll look exactly alike. Okay? So what has happened? What does this graph, what did it do to the graph of f of x? It went what direction? From -6 to 2. That goes to the right. So this graph with the -8 in it has been shifted to the right to give you the same thing you would get if you had an input of 2. Okay? So, I don't know. To be honest, the best way I think is to just remember that. Okay, now I got both of them. So what do we got? 10 right, 10 up. Okay? 3 right, 8 up. 9 left, 4 up. Okay, so these are the easiest ones. 6 left, 6 up, right? So you can kind of go, okay, now we get to these. Now, so that's the add or subtract. So you can add or subtract on the inside, and that moves it this way, and it's opposite. Add or subtract on the outside, that moves it up and down. Okay, now what happens when you multiply? It stretches or shrinks. Now, same rule applies. If it's on the inside, it's the x, so it's going to be horizontal, right? The x is this way, so it's going to be horizontal, but is it opposite when it's on the inside? What do you think? So what's your guess for this one? Stretch horizontally. No. When it's on the inside, it's the opposite. Just like the -8 goes right when it's on the inside, when you think minus would be left, anything on the inside is opposite. Just remember that way. So if it's a 2 or a 3, so what would make it actually stretch then on the inside? Not a negative, 1/2 or 1/3 or 1/4. Negative does something else. Negative switches it, reflects it. Okay? All right, so that should have been a shrink. Okay, so now we're back to this. 10 right, 6 up. 10 right, 6 up. Okay, so what's this one? Stretch horizontally. Now what that means, it's going to stretch by a factor of 6. So that means if you were going to go like from this piece of the graph to this piece of graph was 2 wide, it'll now be 12 wide, right? To go from this point to this point. That's what that means with the stretch, okay? All right, so this will be a shrink horizontally. Okay, what's that negative do? Horizontally. It's on the inside, so it's going to be on the x, so it's going to be horizontal, and it's going to reflect it horizontally, which means across the y-axis. It's going to reflect across the y-axis, okay? Well, I'll show you. So if we had this picture right here, and we wanted to reflect that horizontally, this point is 2 away from here, it would flip over to here. Okay? This point right here, that's 1 away, would flip over to there. This point right here, that's 1, 2, 3, 4 away, is going to flip over 1, 2, 3, 4 over here. Make sense? This is something you're going to do on your homework today. This point right here that's at -5 is actually going to be over here at 5. This point here that's at +5 will actually be over here. So you kind of see what's happening. This point that's 2 is going to be over here at -2. So we would get, oops, this would kind of come down like so, boom, and then straight up like that. That would be a reflect horizontal. But I think basically the best way is the x's become opposite. Think about it, it's x versus -x, right? So when the x is positive will now be negative, and the x is negative will now be positive. They just switch over there. Okay? All right. So that's what that would look like. Okay, what's that doing the negative on the outside? It's going to be vertical. When it's on the outside, it affects the y. When it's on the outside, it's vertical, right? Either a vertical stretch or a vertical shift up and down or a vertical reflection. So it's going to reflect across the x-axis, and then that'd just be the opposite, right? If you got a y up here that's 4, it'll now be down here at -4, right? You got a y that's up here at 6, it'll now be down at -6, okay? So this one, what was this? Up 5. Now we just got a variety of them. This one's down 2, right? What was this one? Shrink horizontally because it's on the inside, right? So that's IXL B1. So you guys could do that. I'm just going to leave that as kind of an optional thing if you want some practice, because you are going to have to answer some questions about those on the quiz, right? There's going to be some of that in your homework too. Okay, so you're going to have some different ones here that they're going to give you combinations of those. They're going to give you a graph like this, and then you're supposed to draw. They're going to give you this graph, and then you're supposed to draw what the new one would look like. Okay, all right. That's all I have for that. Okay, let me.
How long is the quiz?
I give you the whole time. Most quizzes I give you the whole time. Probably the soonest. I mean, some quizzes there'll be somebody maybe get done in 30 minutes. Seems like there's always somebody who uses the whole. If I give you 85 minutes, they use 85 minutes. If I gave them 4 hours, they'd probably use 4 hours. I don't know. But so it'll be 85 minutes. We'll get or 80 minutes or whatever time is. Will we get to use calculators? Yes, we'll get to use calculators because I want you to be able to on your graph. I want you to be able to type in an equation and graph it and so forth. We'll do more of that tomorrow, actually. There's not going to be much with calculators you'll do in this section. Okay, turn to page 20. Turn to page 20. Periodic, last thing, periodic function. Now, if I ask you to describe for me a periodic function, what would you say? Huh? Sine graph. You think of the sine graph. If you were going to describe it to somebody who didn't know what a sine graph was, what would you say? Periodic function is what?
So you know that thing you see in movies all the time with like radio waves and stuff? It's that thing.
Okay, so like something like that.
Yeah.
One of those kind of things, right? Okay, like an EKG or somebody hooked up to a heart monitor or whatever. Okay, what else? Will be another description. You haven't used the word that usually comes up. If you, in one word, you could describe a periodic function. Repeats. Repetitive, repeats. That's the one I get a lot. It repeats. Now, you got to be careful about repeats. Like, for example, I had this graph up here earlier. Would that be a periodic function if it kept going like that? A lot of you are shaking your head. No, that's right. It's not. Because it doesn't repeat what? The same outputs, the y values. That's what it has to repeat. So that would kind of have a pattern, I guess, but the y values are getting bigger and bigger. So that would not be a periodic function. It has to repeat the same y values. So here is actually the simple definition of a periodic function. A periodic function is something that for all x, this would be true. And what this is saying is that if you take a graph and you shift it, now you can put a plus or minus there, and P can be positive or negative. But if P was a period, if you shift that graph left that many units or right that many units, either way, what you get is the same output every time. So that's a really simple way to say it. But if you want to write it out in words, that's not a bad idea. It repeats outputs at specified intervals, and that specified interval is the period. Now, you guys mentioned the sine graph. Okay, what's the period of the sine graph? 2 pi. And the reason for that is every 2 pi it repeats. Now, you got to be careful because at some places it repeats every pi units, right? Because this is pi, and this is 0, and this is 2 pi. So if you only looked at the x-axis, you'd be saying, oh, wait a minute, every pi it gives you 0. But that's not true up here, is it? Right here, that's a 1. When's the next time it gives you a 1? That's at pi halves. What's the next time it gives you a 1? That would be at 5 pi halves, right? So you've got to be careful. Yeah, every pi units it repeats, but that's only for that value of 0. And it does it for other points too, not just the peaks, like right here. Here is a point, and there it repeats again. Now, it does hit that point here, right? I mean, it hits that point again here at a value that's not the period, but that doesn't matter. The point is, every 2 pi we can always get that value out again. Okay? So the period for that is 2 pi. Now, they're going to ask you some kind of goofy type questions with period, and I may also on the quiz. But if a function is periodic and you know it repeats those values. Oh, I got one other part that I forgot. I got to go back and talk about it. If you know it repeats those values, so let's forget the sine function. Just forget, let's just say we're talking about some generic function that's periodic, some generic function f. And what if I tell you that f of 2 is 5? And I tell you that the period is 7 for that function. Okay? So some function, the period is 7, and I tell you f of 2 is 5. What other values of that graph could you tell me? F of 9 would be 5. What's another one? Yes. What else? F of, and we can just go all day, right? You see what they're doing? They're just adding 7 on to those x values, because that's what we're saying. When you move over that many x units, you get the same y value out again every time. So if the x value of 2 gives me 5, then add 7 onto that. 9, add another 7, 16, 23, 30. I just keep going. I'm going to get 5 every time. Do I know any other values of that graph? I didn't tell you anything else about the graph. So do I know f of 4? No. F of 5? No. F of 6? No. But there's a bunch of them I do know, right? I mean, so that's thinking of periodic in a little different way. We're so tuned into thinking of the sine graph and 2 pi and that kind of period. Just understand what that means, periodic. Okay, the thing I forgot that I skipped over was even function and odd function. That's another thing we got to talk about here real quick. So even function and odd function. This is really good information to know. Now, a lot of functions aren't either one. Understand that a lot of functions are not periodic, and a lot of functions are not even or odd. But if they are, it tells us something special about them, and it can be helpful. What's an even function? What are some things you remember about an even function? I'll give you a hint.
If you put it in negative, you get positive.
No, you're on the right track. These are both even functions. And let me tell you another even function. The cosine function is an even function. These are all even functions right here. They reflect across the, but not the x-axis, the y-axis. They have y-axis symmetry, we call that. They are mirror images in the y-axis. I think what you were getting at, Max, was
If you make your output or your input negative, using your output instead of the same,
yes.
it would be positive.
Here's what I usually say with that. Opposites in, same out. Now let's give an example of that. Opposites in, same out. So, for example, on x squared, if I put in a 2, I get out a 4. If I put in a negative 2, I also get out a 4. Does that make sense? That's what you would get. So I put a 2 or a negative 2 in, I get out a 4. Now, but it wouldn't be positive. You said positive. Here I put in a 2, I get out a negative 4, let's say. Right? And I put in a negative 2, I also get out a negative 4. The idea is you put opposites in, you get the same out. Now, here's how that's written in more precise language. Okay? If I put opposites in, I get opposites out. Now think about this with what we were just talking about reflecting. It goes to what Will said with y-axis symmetry. This is saying what? When you put a negative in here is what? Flipping it this way, right? So this is saying if you flip it this way, you get the same thing as if you didn't flip it at all, right? So if I took the cosine graph and I flipped it like that, it would just land right on top of itself, right? If I took x squared and flipped it, it would do this. Now, the reason even kind of has its name is x squared is an even function. X to the 4th is an even function. X to the 6th is an even function, right? Now, if you shift those at all, then they might not be anymore. Like if I take x squared and shift it to the right 2, that is not an even function anymore, right? Because now it's over here and it does not have that symmetry anymore, right? It doesn't have that y-axis symmetry. So if you shift it, it's not an even function anymore. But your basic x squared graph has that. Okay, odd function is kind of the reverse. Do you remember what the symmetry was on the odd function? It's origin symmetry. It's not, a lot of times people want to say x-axis. Well, that's actually kind of silly anyway, because what would x-axis symmetry look like? It wouldn't even be a function, right? You can't have x-axis symmetry. It wouldn't even be a function, right? It's origin symmetry. If you put opposites in, you get opposites out. So in other words, if you put in a 2 and get out a negative 7, when you put in a negative 2, you should get positive 7. Now, not the opposite of what you put in, but what we mean is if I put in a 2 and get something out, when I put in a negative 2, I should get the opposite of that out. Whatever I got when I put in the 2. And the way we write that is this way. We go f of negative x is equal to negative f of x. Right? That's opposites in, opposites out. Now, think if you're shifting, this is saying if you took the function and rotated it this way, you get the same thing as if you would have flipped it this way. Well, that's what origin symmetry looks like. Now, that would be an example, that would be x cubed. Think about x cubed. If you flip this down, right? Let me do it in blue over here. If I flip this vertically, I would end up with this. But isn't that the same thing as if I flipped it horizontally? If I took this thing and flipped it horizontally, I'd get this same thing, right? So that's kind of what that is saying. But I usually think it was opposites in, opposites out. Okay, the other one that's an opposite function or an odd function is a sine function. That has origin symmetry also. So you come over here, you put something in, you get that out, you put opposite in, you get opposite out. Opposite in, opposite out. Okay? Okay. But a lot of functions aren't either one. Just understand, right? All right, even, odd, periodic, a lot of terminology here. All right, so there are some IXLs that can be good on these B1. If you're not sure on those stretches, another thing those are called are dilations. So if you're not quite sure on these, you want to practice those a little bit. That would be a shrink horizontally, right? So you've got some of these. These are optional if you want to try them. This one, B5 and B6, kind of throw them all together so you get some practice at different ones. So those aren't bad practice as well. But your assignment is 1.2 homework, okay? So you can go ahead and get started on that. You're going to have a lot of those questions. I'm going to say, how are these graphs related? That's when they're talking about that shift. How are these graphs related? Well, it's a shift right of 3 or something, and you're going to be doing those. And there might be some where you draw some sketches. I definitely want you to draw some sketches on 35 through 40, that section. 35 through 40 is where you're doing this. They give you this picture here. Okay, they give you this picture here, and then you have to stretch it or shrink it or something, and then redraw it. So make sure you're doing that. They don't, and those aren't in the answer book here, but 35 through 40. So.